Hi, my name is Desmond Phillips 23806 from Group 14, and I'm going to discuss about the sensors in our IFTP project. The sensors that we have used in this project is heart rate sensor, temperature sensor, and ECG sensor. As for the design analysis, we have used heart rate sensor of plug and play type, and for the temperature sensor we have chosen LM35, and for ECG sensor we have chosen AD8232. The specifications are as shown in the table. For the methodology, sensors are first connected to the microcontroller before the data are taken from the sensors and transmitted to the microcontroller to be processed. And then the data is displayed on the serial monitor, and then the data is sent to the cloud. For the proof of concept, we have developed an application that shows the outputs. So in the first image, we can see the graph of ECG signal. In the next image, we can see the body temperature around 36.70186, and at the bottom of proof of concept, we have another image showing the heart rate at 83 bpm. That's all from me. Thank you.
Assalamualaikum, I am Nabil and I am in charge of power management for Hawa wearable device. Before we integrate, I did subsystem test to check how much the battery capacity of the 3.7 lithium ion batteries. The battery capacity test will measure the voltage across the load and the current flow. To calculate the capacity, the test is measured for each milliseconds until it ran out of battery. From the test, we can obtain the plot of voltage versus discharge capacity as shown in the left figure. Test 1 is tested when the battery is not fully charged, but test 2 and test 3 battery were charged before tested. You can also refer to appendix in the report to see the raw data of another 2 tests. This battery capacity test will be used to rough estimate how long the battery will last and ranging voltage percentage according to the uh, battery voltage value when the subsystem integrate. This is the overall system design and a simpler graphical representation of the overall system. Two 3.7-volt batteries is used to supply both Arduinos. Firstly, the voltage sensor will measure the battery voltage. If the battery voltage does not meet the minimum operating voltage that we have set, the rest of the sensor load is in off mode and it will prompt a low battery indicator in the app. If the battery voltage is sufficient, all sensor will operate in on mode. The voltage sensor will also provide the battery percentage of the device. When it is on mode, the current sensor will start to measure the voltage, current and power consumption of the load. From the current usage, we can obtain the estimated battery life of the system by referring to the discharge capacity from the battery capacity test. Battery percentage, battery life, and total power consumption are displayed in the app for user to view. Thank you.
Assalamualaikum and good morning to everyone. I'm Arif, the one who is responsible for indoor positioning subsystem. So the objective of having indoor positioning subsystem for the device is to locate the position of the user in indoor environment. So to achieve this objective, the subsystem is designed by using RSSI signal from Wi-Fi access points. However, there are some issues when using RSSI signal, which are the signal fluctuations in indoor environment. They are caused mainly by signal refraction of the walls and interference from other Wi-Fi routers. So to solve this issue, calibration of the access points are conducted. Initially, 4 access point or APs, which are the non-MCU ESP8266 Wi-Fi modules, are programmed with predefined SSID for each one of them. Then the APs need to be calibrated at 1 meter distance, and the calibration results are analyzed as per shown in this line graph. And the calibrated RSSI for each APs are tabulated and programmed in another non-MCU ESP8266 in station mode. And the results on the mobile app shows that the movement of the user in the kitchen from point A to point B as per intended design for the device. The movement of the user is animated from the previous location to the next location. So that's all from me. Thank you.
Hi, my name is Muhammad Rosli and I'm handled on human recognition. So now I explain a bit about the methodology. The sensor I use is the MPU6050 gyro accelerometer, and the way it works I dump the code of its functionality on the Arduino IDE and then connected it with the sensor, and then I will turn on the serial monitor in order to see the serial data and also make the condition based on the human activity that I need. So and then I will make more analysis and more analysis to verify the data. So the second part is the table. So this is the raw data. It consists of an angle and acceleration. Here is a raw data. It's like an amplitude. So by putting this condition of angle and acceleration, I will name it as specify it as the human activity as time. So the actual angle is actually 90 degrees Celsius and the 90 degree, and actually the acceleration is 0 meter per second squared since standing is not moving. So this is all the data. So based on here, I have run more than 10 run, which each run will consist of 20 cycles. So the result of this validation process will be explained more on the result part. So for the result and discussion here, I have successfully achieved the 4 activity, which are stand, lying, falling, and walking. So as you can see, this is a stand, lying, walking, and falling. So in order to determine the consistency, so I have done a long run, more than 10 run. So this is the average data for each run on the 20 cycle. For standing and lying, I think the result is acceptable, it's doing good, more than 17%. And then for walking, it's also more than 70%, but for falling, it's a bit harder. So the true data average is 9 and the false is 11. Okay. Next is the communication and mobile apps, also handled by me. So the methodology for communication, and I split it with the mobile application since we cannot use the built-in application, so it's a bigger task for me. So for communication, we have two ways of communication, which are transfer data and also retrieve data. So I transfer data from microcontroller to cloud and retrieve data from cloud to mobile application. So the cloud that I'm using is the Firebase cloud. Okay. And then for this communication part, there's some additional, which is I write it in the report. I'm using the serial communication between the MCU microcontroller and also the Arduino in order to make the data to be sent to the cloud. This is due to the Firebase library is only compatible to dump with the not MCU and cannot compatible with the Arduino. So I need to use the serial communication for mobile application. Okay, I'm using the Android Studio there. So the language I'm using to code is the Java language. As you can see from the workspace, the left side is the code platform, and I'm using the Java language. The right side is the design part. So there's two types of file, which is the .java is for the coding for the functionality, able to retrieve data or something, or click button to a new page. And the second file is the .xml file, which is needed to design the interface of the mobile application. So for here is the result and discussion for the communication. So I need to differentiate on the priority level on transferring the data from the microcontroller to Firebase. So here I already made the priority level for each data. So the lowest priority is the battery life, since we know they can have delay in order to send the data. But the data that is very important is the ECG, because we need to send the data in instant. We cannot be delayed. So by using Firebase, we only receive a delay maximum average of 2 seconds, and average usually is 1 second. So that's the important of the priority. And then I found out that when I'm using the Node MCU in order to transfer the data from Node MCU to the cloud, it is cause a delay average of 12 seconds. So the best solution is I'm using the microcontroller more than one, not MCU, and which is, as you can see here, the first microcontroller I split it, the data, I send the BPM, ECG, and body temperature. So the latency become improved 1 second and 1 second to 2 second and 1 second. So for the human recognition, also 1 second to 2 second. For window positioning is 1 second. As you can see, for the latency of the retrieving data from Firebase of the mobile application is not cause any problem. It is very efficient. It is all of the data received is average of 1 second. Okay, now we proceed with the design discussion for mobile application. As you can see, the mobile application is successfully developed. There are 6 layouts altogether. So here the first one is the main menu layout, and then this battery layout, window positioning layout, body temperature layout, and this layout is the combination of the pulse and also ECG. There's the ECG signal when it's running, and also the last one is the human recognition layout. So now we already successfully integrate. So before we proceed with our live demo, I will present you the video for our integration. So enjoy.